Welcome to this problem walkthrough. Today, we'll explore LeetCode number 1391, check if there is a valid path in a grid. This problem challenges us to determine if there's a valid path from the top left to the bottom right corner of a grid, given certain constraints. Let's dive in and break it down step by step. In this problem, we are working with an MXN grid where each cell has a specific type that determines how you can move from that cell to its neighbors. There are 6 different types of cells, each defining unique movement paths. For example, Type 1 allows movement horizontally, connecting to the left and right neighbors, while Type 2 allows vertical movement, connecting to the top and bottom neighbors. Types 3 through 6 represent corner connections, where movement is only possible in specified diagonal directions, such as from the top left to the bottom or from the bottom right to the top. The goal is to determine if there is a valid path starting at the top left corner of the grid, at position 0, 0, and ending at the bottom right corner, at position M1, N1. The input is a 2D list where each cell contains an integer from 1 to 6, representing its type, and we need to return a boolean indicating whether such a path exists. To solve this, our task is to check if there is a valid sequence of moves that connects the top left corner of the grid to the bottom right corner. If such a path exists, we return true. Otherwise, we return false. Let's look at an example to clarify this. Consider a grid where the first row contains cells of types 2, 4, and 3, and the second row contains types 6, 5, and 2. Starting at the top left cell, which is type 2, we can move vertically. This leads us down to the second row's first cell, which is type 6. The type 6 cell allows movement to the bottom right or the top right, so we move to the right. Now we are at a cell of type 5, which allows movement to the bottom left or the top left. From here, we move upwards to the first row's second cell, which is type 4. Following the valid connections, we move right to the next cell, which is type 3, and finally move down to the bottom right corner. Since we successfully reached the target cell, the output is true. In another example, consider a grid where the first row contains cells of types 1, 2, and 1, and the second row contains the same sequence. Starting at the top left corner, which is type 1, we observe that the movement is restricted to horizontal paths, so we can only move left or right. As we progress, there is no connection that allows us to move downward to the second row and ultimately reach the target cell at the bottom right corner. Since it's impossible to connect these paths to the destination, the output in this case is false. Now, let's explore a third example with a grid that consists of a single row containing cells of types 1, 1, and 2. Starting at the initial cell, which is type 1, we can move right to the next cell since type 1 only allows horizontal movement. At the second cell, which is also type 1, we again move right to the final cell in the row. However, the final cell is of type 2, which allows only vertical movement, and there are no rows below to connect to. Consequently, it's impossible to form a valid path to the bottom right corner, and the output is false. These examples highlight the importance of understanding the grid structure and how the types of cells influence movement. There are a few constraints and edge cases to keep in mind when solving this problem. First, the grid size can range from as small as 1 by 1 to as large as 300 by 300, so the algorithm must be efficient to handle larger grids. Additionally, the value of each cell, which determines its type, will always be between 1 and 6. Edge cases to consider include grids of minimal size, such as a single-cell grid, where the path is always valid since the start and end points are the same. Another edge case is when paths are disconnected due to cell types that don't align with their neighbors. Lastly, a fully connected grid, where all cells are of type 1 or type 2, may or may not form a valid path depending on the overall orientation. By addressing these constraints and edge cases, we can ensure our solution is robust and handles all scenarios effectively. To solve the problem of checking if there is a valid path in the grid, we need to consider the unique challenge posed by the grid structure. Each cell in the grid has a specific type, and the connections between cells must follow the rules defined by these types. For example, some cell types allow horizontal movement, others allow vertical movement, and some enable diagonal transitions like left to down or right to up. This means our solution must carefully evaluate the connectivity between cells while adhering to these constraints. To tackle this, we explored various approaches, each with its own strengths and trade-offs, which we will now discuss. The first approach we considered is a brute force method using either depth-first search, DFS, or breadth-first search, BFS. In this approach, we treat the grid as a graph where each cell is a node, and valid connections between cells act as edges. Starting from the top left corner, we explore all possible paths to determine if there's a way to reach the bottom right corner. Using DFS or BFS, we systematically traverse the grid, ensuring that each movement between cells satisfies the rules defined by their types. While this approach is simple and intuitive, it can become inefficient, especially for larger grids, as it may repeatedly check cells that have already been visited. This leads to a time complexity of O(m*n) and a space complexity of O(m*n) to keep track of visited cells. However, this method's primary drawback is its inefficiency due to redundant checks, which we aim to address in optimized solutions. An optimized approach we explored is based on the union-find data structure, also known as disjoint set union. This method pre-processes the grid to group connected components, where each component represents a set of cells that are reachable from one another. By doing this, we can quickly determine if the top left and bottom right corners belong to the same connected component. The process involves initializing a union-find structure for all cells and iterating through the grid to check valid connections between a cell and its neighbors. If two cells are connected based on their types, we merge them into the same component. This pre-processing step allows us to answer the connectivity query efficiently. The time complexity is O(m*n)alpha, where alpha is the inverse Ackermann function, and the space complexity is O(m*n). While this approach is efficient, especially for scenarios with multiple connectivity queries, it is more complex to implement compared to BFS or DFS. The strategy we ultimately chose is BFS with a valid movement check. BFS provides a systematic way to traverse the grid step by step, ensuring we only follow valid paths. This approach is particularly well suited to this problem because it directly aligns with the goal of determining a single valid path from the top left to the bottom right corner. To implement this, we initialize a queue with the starting cell and maintain a visited set to avoid redundant processing. For each cell, we evaluate the possible movements based on its type, and if a move is valid and the destination cell hasn't been visited, we add it to the queue. If we reach the bottom right corner during this traversal, we return true. Otherwise, if the queue is exhausted, we return false. This method is efficient with a time complexity of O(m*n), as each cell is processed only once, and it's straightforward to implement compared to union find. The space complexity of the BFS approach is O(m*n), which accounts for the queue and the visited set. We chose BFS for its simplicity and effectiveness in solving this specific problem. Unlike union find, which is more suitable for scenarios requiring multiple connectivity queries, BFS directly addresses the task at hand without unnecessary complexity. It also handles edge cases, like disconnected segments, naturally. In comparison to DFS, BFS avoids the risk of stack overflow on large grids and provides a more structured traversal. While BFS may be slower than union find for very large grids, it strikes the right balance between simplicity and performance for the single-path connectivity check. Overall, BFS is intuitive, easy to debug, and well-suited for this problem, making it the preferred approach. To solve this problem, we need to determine if there is a valid path from the top left corner of the grid to the bottom right corner. The grid is essentially a network of streets, where each cell contains a specific street type, numbered from 1 through 6. These street types dictate which directions you can move in and out of that cell. The key challenge is to simulate movement through the grid while ensuring the path remains continuous. This means that the direction you exit one cell must align with the direction you enter the next cell. We can think of the grid as an implicit graph, where each cell acts as a node and the valid movements between cells represent edges. To explore this graph efficiently, algorithms like breadth-first search or depth-first search are highly suitable. Additionally, we must account for edge cases, such as very small grids, streets with no valid outgoing paths, or scenarios where there are multiple disconnected sections of the grid. Addressing these considerations is crucial for building a robust solution. The algorithm begins with input parsing, where we extract the grid dimensions and structure while handling edge cases like empty grids or single-cell grids. Next, we define the movement rules for each street type. For example, street type 1 allows movement left and right, type 2 allows movement up and down, and so on. These rules are essential for verifying valid paths during traversal. Once the street connections are mapped, we prepare for the graph traversal. Using either BFS or DFS, we aim to explore the grid systematically. To avoid revisiting cells, we maintain a visited matrix. Additionally, a queue for BFS or a stack for DFS will store the current cell and its entry direction, ensuring we can keep track of our progress through the grid. This preparation lays the groundwork for simulating movement while adhering to the rules of each street type. In the breadth-first search approach, we start by initializing the queue with the top left corner of the grid, along with its entry direction. While the queue isn't empty, we process cells one by one. For each cell, we examine its neighbors to identify valid movement paths. This involves checking if the neighbor is within grid boundaries and, more importantly, verifying that the current cell's exit direction aligns with the neighbor's entry direction based on our predefined street mapping. If the conditions are satisfied, the neighbor is marked as visited and added to the queue for further exploration. The traversal continues until we either reach the bottom right corner, confirming the existence of a valid path, or exhaust all possibilities, indicating that no valid path exists. The termination condition ensures that we return true if the bottom right corner is reached, or false if it isn't. To implement this solution effectively, we rely on specific data structures. A visited matrix is used to track which cells have already been processed, preventing redundant exploration. The BFS queue stores the current cell along with its entry direction, allowing us to maintain context during traversal. Additionally, our movement rules for each street type are encoded in a mapping dictionary, enabling quick validation of entry and exit directions. To optimize the algorithm, we can implement early exit by stopping the traversal as soon as we reach the bottom right corner. Directional filtering further reduces unnecessary checks by limiting neighbor exploration to only those that are valid based on the current cell's exit directions. From a complexity perspective, the algorithm's time complexity is O(m*(n), as each cell is visited at most once. Similarly, the space complexity is O(m*(n), accounting for the visited matrix in BFS queue. These optimizations ensure the solution is both efficient and scalable for larger grids. Here, we start by importing the D class from the Collections module, which will help us implement a breadth-first search. Next, we define the solution class and the hasValidPath method. Inside this method, we first determine the dimensions of the grid using len grid for the number of rows and len grid 0 for the number of columns. We then define a dictionary named directions, where each key corresponds to a street type, and the value is a list of possible movements from that street type. For example, Type 1 streets allow horizontal movement to the left and right, while Type 2 streets allow vertical movement up and down. We also define a helper function as _connected, which checks if two street types are compatible for movement in a given direction. This ensures that the path remains valid as we traverse the grid. Then, we initialize a 2D list visited to keep track of the cells we've already processed, marking all cells as unvisited initially. We also initialize a queue with the starting cell, 0, 0, and mark it as visited. The while loop begins our traversal, where we repeatedly dequeue a cell and check if it is the target cell, M1, N1. If it is, we return true, indicating that a valid path exists. Next, we iterate over all possible directions for the current cell street type, as defined in the directions dictionary. For each possible direction, we calculate the new coordinates NX and New York by adding the direction offsets DX and DY to the current cell's position. We then check if the new position is within the grid bounds and if the cell at NX, New York, has not been visited yet. If both conditions are satisfied, we call the is_connected function to check if the current street type and the new street type are compatible in the given direction. If they are connected, we mark the new cell as visited and append it to the queue for further processing. This continues until either we find a valid path to the bottom right cell, in which case we return true, or the queue is exhausted, meaning no valid path exists. In the latter case, we return false. This ensures that the algorithm explores all possible paths systematically while avoiding cycles using the visited list. Here, we start by importing the necessary packages and defining our solution class. The main method, hasValidPath, takes a 2D grid as input, where each cell contains a street type. First, we determine the dimensions of the grid using M and N. Then, we define a map called directions to represent the possible movements for each street type. For example, street type 1 allows movement left and right, while street type 2 allows movement up and down. Each street type is mapped to an array of direction vectors that define valid movements. Next, we define a helper function, isConnected, to check if two street types are connected. This function compares the direction from the current cell to the next cell against the directions supported by the next cell's street type. If a match is found, the two cells are considered connected. Finally, we initialize a visited array to keep track of the cells we've already processed, and we define a queue to use for our breadth-first search traversal. We begin the traversal by adding the starting cell, located at the top left corner of the grid, to the queue and marking it as visited. The breadth-first search loop runs as long as the queue is not empty. Within the loop, we dequeue the current cell and check if it's the bottom right corner of the grid. If so, we immediately return true, as we've found a valid path. Otherwise, we iterate over all possible directions for the current cell's street type. For each direction, we calculate the coordinates of the next cell. We ensure the next cell is within grid boundaries and hasn't already been visited. Then, we create a reverse direction vector to check if the next cell connects back to the current cell using the isConnected function. If the next cell is connected, we mark it as visited and add it to the queue to continue the search. This process ensures we explore all valid paths through the grid while avoiding cycles. Finally, if the queue is exhausted and we haven't returned true, it means no valid path exists from the top left to the bottom right corner of the grid. In this case, we return false. This completes the implementation of the hasValidPath method. The algorithm effectively uses breadth-first search to explore all possible paths while leveraging the directions map to ensure the movements align with the street types. By checking connectivity between cells and avoiding revisiting nodes, we maintain both correctness and efficiency. To solve this problem, we need to determine if there is a valid path from the top left corner of the grid to the bottom right corner, following specific movement rules defined by the grid's street types. In the first example, the grid has dimensions 2 by 3, and we initialize the visited matrix to keep track of cells we've already processed. Starting at 0, 0, we mark it as visited and add it to our queue. The street type at 0, 0 is 2, which allows vertical movement. Since moving up is invalid here, we can only move down to 1, 0. The connection is valid because the street type at 1, 0 allows upward movement, so we mark 1, 0 as visited and add it to the queue. Next, we process 1, 0, which has a street type of 6. This type allows movement to the right and upward. Moving upward leads back to an already visited cell, but moving right to 1, 1 is valid since the street type there allows a leftward connection. We then mark 1, 1 as visited and enqueue it. Finally, processing 1, 1 reveals that its street type allows movement to the left and upward, but neither direction leads to new cells. At this point, the queue is empty, and we have not reached the bottom right corner. So, the output for this example is false. In the second example, we have a grid with dimensions 2 by 4, and the task is the same. Starting at 0, 0, we initialize the visited matrix in queue. The street type at 0, 0 allows horizontal movement, so we move right to 0, 1. This is valid because the street type at 0, 1 also supports a connection back to the left. At each step, we continue moving rightward through 0, 2, and 0, 3, because all the street types in row 0 allow seamless horizontal movement. Once we reach the end of row 0, we can move down to 1, 3, because the street type at 0, 3 connects downward to the street type at 1, 3. In row 1, the street types allow horizontal movement to the left. As we traverse leftward through 1, 2, 1, 1, and finally 1, 0, the connections remain valid. By following this path, we successfully visit the bottom right corner of the grid. Therefore, the output for this example is true. In the final example, we have a single-cell grid where the only cell is 0, 0. Since the starting point and the end point are the same, there is no need for any movement. During initialization, we mark the single cell as visited, and because we've already reached the endpoint, the result is immediately true. This demonstrates that even in the simplest cases, our logic works correctly to identify a valid path. The output here is true. The time complexity of this algorithm can be broken down into three main components. First, the breadth first search, or BFS, is used to traverse the grid starting from the top left corner. Since each cell in the grid is visited at most once, and there are m times n cells in the grid, the BFS traversal contributes O(m*(n) to the overall time complexity. Next, for each cell, the algorithm checks the directions allowed based on its type using a dictionary. This lookup is constant, or O(1), because the number of directions for any cell type is fixed at a maximum of 4. When extended across all cells, this operation still adds up to O(m*(n). Finally, the algorithm verifies connectivity between cells using the is_connected function, which checks if the reverse direction exists for the neighboring cell. This check is also a constant time operation, or O(1), and when performed for every neighbor of every cell, it also totals O(m*(n). When we combine these three components, the overall time complexity remains O(m*(n). The space complexity of this algorithm can also be analyzed in several parts. First, the visited matrix is used to track which cells have been processed. Since this matrix has the same dimensions as the grid, it requires O(m*(n) space. The BFS queue, which stores the cells to be processed, can grow to contain all cells in the grid in the worst case, such as when all cells are connected, contributing another O(m*(n) to the space complexity. The directions dictionary, which maps each cell type to its valid movement directions, is a fixed-size data structure with just 6 keys, so it uses constant space, or O(1). Finally, any temporary variables, such as those used for coordinates, require negligible space and are considered O(1). When we sum these components, the total space complexity of the algorithm is O(m*(n). Now, let's analyze the best, average, and worst cases. In the best case, the start and end points are directly connected, such as in a small grid with a valid path. Here, BFS terminates almost immediately after visiting just a few cells, resulting in time and space complexities of O(1). In the average case, BFS explores part of the grid before finding the destination. Although fewer cells might be processed compared to the worst case, the potential to visit all cells means the time and space complexities remain O(m*(n). In the worst case, the grid is fully connected, and the algorithm must traverse every single cell once before reaching the destination. This scenario also leads to O(m*(n) for both time and space complexities. Comparing this to a brute force approach, which might enumerate all possible paths and have an exponential time complexity of O for (m*(n), our BFS-based solution is dramatically more efficient. Additionally, BFS is preferred over DFS in this context because it guarantees the shortest path is found first and avoids the extra stack space required by recursion in DFS. Finally, let's summarize why the algorithm's time and space complexities are both O(m*(n). The dominant factor here is the size of the grid itself, as every cell contributes a constant amount of work and must be processed exactly once. Operations like direction lookups and connectivity checks are performed in constant time, or O(1), which does not affect the overall scaling. This means that as the grid size grows, the time and space requirements grow linearly with the number of cells in the grid. Therefore, both the time and space complexities are conclusively O(m*(n), as demonstrated in the earlier breakdown. When solving this problem, there are a few common mistakes to watch out for. First, not handling all 6 street types correctly is a frequent issue. Each street type has specific entry and exit directions, so if you miss accounting for any of these, your path validation will fail. A good fix for this is to create a map or table that explicitly defines the valid incoming and outgoing connections for each street type. Another common mistake is ignoring the grid boundaries. For example, attempting to move outside the grid, like accessing grid -1, 0, or grid I, j, when I or j is out of bounds, can cause runtime errors. To avoid this, always check that the next position is within the grid's limits before proceeding. Additionally, revisiting cells without marking them is another pitfall. If you don't use a visited set or mark cells directly, you risk infinite loops in DFS or BFS, leading to wasted time and duplicate exploration. By marking visited cells, you ensure an efficient traversal process. Another mistake developers often make is overcomplicating their implementation. Writing too many if-else conditions to handle the directions not only makes the code harder to debug but also increases the likelihood of errors. A better approach is to use a direction map or dictionary to simplify the navigation logic. It's also important not to misjudge the problem's complexity. While this is fundamentally a graph traversal problem, the grid's relatively small size means that simpler algorithms like BFS or DFS are typically sufficient. Over-engineering the solution with advanced graph algorithms like Dijkstra is unnecessary here. Instead, the focus should be on implementing BFS or DFS efficiently and making sure your solution is both correct and easy to understand. In interviews, understanding the problem's constraints is crucial. For this problem, the grid size, which can go up to 300 by 300, ensures that BFS or DFS is feasible. There's no need to overthink or complicate your solution. Clearly explain your approach, emphasizing that this is a graph traversal problem where grid cells represent nodes and the streets define edges. Highlight how BFS or DFS can be used to determine whether there's a valid path from the start to the end. Clarity is key, so use concise data structures like direction maps to represent valid movements. This not only simplifies your code but also makes it more readable. Be prepared to discuss edge cases as well, such as grids with only one cell, grids with no valid paths, or grids with disconnected components like islands. These are all scenarios interviewers might ask about to test your understanding. This problem shares similarities with several other LeetCode problems. For instance, LeetCode 200, Number of Islands, also involves exploring connected components in a grid. LeetCode 130, Surrounded Regions, focuses on connected regions and boundary conditions. LeetCode 994, Rotting Oranges, is another BFS problem that involves grid traversal and adjacency logic. Lastly, LeetCode 785 is Graph Bipartite, tests graph traversal algorithms like BFS or DFS to validate conditions. Apart from these, there are alternative approaches you could explore for this problem. One is the union find algorithm, where each cell is treated as a node, and valid movements connect components. While elegant, this method requires additional space and might be overkill for smaller grids. Another option is backtracking, which recursively explores all possible paths. However, backtracking is often slower and less efficient than BFS or DFS, especially for larger grids. Dynamic programming is another approach you might consider. Here, you store results for each cell to avoid recomputation. However, this method is generally less intuitive and not as space-efficient as graph traversal for this particular problem. Ultimately, the key insight is that this is fundamentally a graph traversal problem constrained by the rules of street types. BFS is usually preferred for shortest path-like problems, but since all paths in this grid are of equal length, DFS works just as well. To make your solution clear and efficient, use data structures like dictionaries to represent movement logic, simplifying your implementation and improving readability. By focusing on these strategies, you can solve the problem effectively while keeping your code clean and easy to maintain. Great work! In this lesson, we covered LeetCode number 1391, breaking down the problem and exploring possible solutions. Remember to keep practicing grid traversal techniques and think critically about which algorithm best fits the problem. Thanks for joining, and see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!